Let's go back to our data and consider a relationship with two predictor variables. So we looked at, was age predicted by the year of the award? And those were two continuous variables. Now let's add in gender as well. So is age predicted by the year and the gender? We might ask, within the men, is there a relationship between age and the year? Has the age increased or decreased over the years? Within the women, is there a relationship between the year and the age at which they win? So we've got a continuous outcome, the age, and we've got one continuous predictor variable, the year of the award, and then we've got a categorical variable, the gender. And so we're going to split it into two groups by gender, and then calculate or visualize it with two XY scatter plots and with multiple correlation coefficients, or in this case, two correlation coefficients. If we had more than two genders, we'd be looking at multiple correlation coefficients and multiple scatter plots. So remember when we looked at a means comparison and distributions, and we saw that we had a bimodal distribution, and we suspected that we had two different groups mixed together. Well, it can be the same idea here. Maybe our cloud of correlation data would make more sense if we split this between the men and the women. Maybe that there's part of this that's just two clouds sitting on top of each other. We're going to start by splitting this into two groups. I'm going to select all of my data and sort by gender. So I've got the females and then the males. And I'm going to copy the data for each of those groups. Remember, it doesn't make a lot of sense to do this other than putting it into SEEIT, but this is the way we need to do it to put it into SEEIT. I'm going to copy that and paste it here. Year of award, actresses, age in years, for actresses. And then I'm going to do the same for the actors. And I'm going to copy that data and put it, let's see, right there. I'll make sure I've got my data labels nicely. Let's go ahead and load this up to SEEIT. I'm going to select it all and copy. I'm going to jump to SEEIT and choose to add a data set and paste. I had a blank column in between them. I wonder what that's going to do. I'm going to give this the label by gender just so that I remember what I'm doing. Okay, it looks like it recognizes that there are just four groups. So we've got the year for the actresses, the age for the actresses, the year for the actors, the age for the actors, and then we've still got the year for all of them and the age for all of them. But let's see if splitting that into two groups by that predictor variable gender is going to make this pattern different, if we're going to be able to see a different pattern. So let's go ahead and visualize this. Does the year of the award for actresses predict the age? And we want to add another. I'm going to click on this two graphs right here. Does the year of award for actors predict the age for actors? It's going to allow us to compare those scatter plots side by side. Ooh, notice that it hasn't put them on the same scale. We can look at them, but we want to show the line of best fit. You can try to draw yours, or we can just ask it to calculate this line of best fit and show the R value and apply to all. And let's see what we get here. Within the actresses, the R is 0.23. So that's become a stronger relationship. And that is a positive relationship where in the earlier years, the actresses were younger. And there is now, as the years have progressed, the age of actresses has increased. For the actors, the R is 0.10. So that's right on the cusp there. It's probably not a relationship. It's probably not a real relationship. It's probably close enough to zero that we wouldn't call that a positive relationship. But let's go ahead and write that up. So we want to capture those two scatter plots, and you want to start with a statement that compares the overall relationship between the variables for each gender, and then you're going to end them each statement with your inferential statistic. That's the way you justify how you're making a conclusion. And then don't forget to include a sentence that interprets this. I'm going to copy these by just taking screenshots of them. On the Mac, you can take a screenshot by holding down the Shift and the Command key and typing the number 4. And that turns your cursor into a little crosshair, and you can click and drag and take a picture. So that's Shift and the squashed bug, the Command key, and then the 4, and then you click and drag to take that picture. Let's think about how we would write those up. I'm going to add both of those screenshots that I took into Word. I'm going to shrink them down a bit so I can work with them. I'm holding down the Shift key while I shrink them to keep the aspect ratio the same. So let's just start with a few notes. So I've started just by saying there's a positive correlation between, and I've named the two variables, and I need to back that up. So I'm going to type in that there's an R equal to, what is that, 0.23, is it? And then we need to write a sentence that interprets that. So in the early years of the Academy Awards, the age of the actresses was, now you need to write a comparison word. Was it younger than today or older than today? So early years, the age of the actresses was younger than it is today. Maybe something like that. And that's this one. However, when it comes to the actors, there does not appear to be a relationship between age at award and year of award. And why are we saying that? We're saying that because R equals 0.1. And then we need to write that sentence that interprets that. The age at which men have won. Best Actor does not appear to be changing over the years.